So hello everyone, thank you so much for being here. It's wonderful to be able to talk to you despite all the current travel restrictions. So as Chair said, I was asked to tell you about using high resolution spectroscopy for exoplanet atmospheres and how we can study them. And so with this talk, I want to take you through the basics of the technique. And if there's time at the end, I'll sort of go a little bit more into some of the science we can do on the dynamic side of atmospheres, but for the most part, I'll be talking about the composition and the structure of the atmospheres. So I want to start with this plot, which is the orbital period versus the mass, which I don't actually think I've seen in this workshop so far, so maybe I get to show it first. And this is an animation from Hugh Osborne that shows you how we have detected planets over the years. We start out with the solar system. You'll see Pluto appear and disappear at various points. And then you start to see all the planets appearing, our Nobel Prize winning 51 Peg planet as well. And you'll see the build-up of the radial velocity planets, especially there in the green, and those transiting ones coming in as well. And I want to show this just to sort of set into context the incredible diversity that has appeared to us through all of our planet searches. And this is sort of borrowing from a plot that actually was made by NASA a while ago that sort of identified these different regions of planets, from hot Jupiters and cold gas giants to ocean worlds, ice giants, rocky planets, and even lava worlds. And then you see we have down there in the bottom right-hand corner the frontier of where we're trying to head towards with extreme precision on radial velocities and transits as well. But whilst we're doing that, we have this whole slew of other exoplanets to characterize. And so that's a lot of the work that I focus on and what I want to tell you about today. So just to make the connection between the extreme precision RV and exoplanet atmospheres and the technique that I'm going to show you today, what we need particularly is high spectral resolution and stable spectrographs, and you'll see as we go through the analysis as to why we need that. But despite all of the wonderful talks this week, there are some things that are going to do that if you work on extreme precision radial velocities, you might feel a bit cringed at. But largely with what we're doing, we can actually get away with wavelength calibration in some parts just from the telluric lines, and that the stellar activity on the level that's been talked about this week in terms of granulation is probably not so much of an issue for us, but certainly flares and pulsations can be, and I'll show you that at the end. But the real connection here is that this atmospheric work relies really on some of the instruments being built for radial velocities, and it's seen a real uptick in the last few years, especially due to the sort of onslaught of all of the new instruments for being able to do high resolution work. And so I list here the instruments that have done, or ones that I know are doing, this atmospheric work, but this is not an exhaustive list. There are certainly more as well. So maybe you recognize your favorite spectrograph in there. Okay, and just to tell you that most of what I'm going to talk about today is contained within this textbook chapter that I wrote that's aimed at a graduate level. So if you want to go back or go further beyond the talk, please take a look at this as well. Most of it is contained within here. Okay, so Natasha gave us this great talk about what we can do with transiting exoplanets, and really they give us the most amount of information because we get the radius. But there might be some stars that don't transit, and that's the majority of them, planets that aren't transiting that stars, that we still want to be able to characterize their atmospheres, and that might especially mean those nearest to us. So what you're seeing here is just a diagram that shows you the different types of stars within our local neighborhood within about 10 parsecs. And you'll see that most of them are M-dwarfs as well. And if you calculate the chances of finding a habitable zone transiting planet, your chance is about 2%. So if we get really lucky, maybe there's about 4 within 10 parsecs that we can characterize with transit spectroscopy, but otherwise we need another way to do this. And just to show you in context of looking at all the different systems that are out there that we know within 10 parsecs that have planets, you can see our nearest one is obviously around Proxima Cen, that's Proxima Cen b, and that has been shown not to transit. And so we might want another technique that we can use to study its atmosphere. And so that's where high resolution spectroscopy comes in, and it really relies on the information content that you get in a spectrum when you go to high spectral resolution. And I'm going to show you that here. So here we're focusing on the carbon monoxide spectral region. So you see there's a spectral bandhead that appears here around 2.3 microns. And what you see here first is one data point in a current Hubble Space Telescope spectrum. Right? So Hubble tends to bin down the data to find the signal, and this represents one of its bins. It's a resolution of about 30 in the final bin spectrum. If you were to observe carbon monoxide, which is typically found in hot Jupiters, at a resolution of around 3000, you'd start to see the continuum, or some sort of convolution of all the spectral lines together. And you start to look like this. But as we increase the resolution, if we say go up to 5000, you start to see actually there's information in here, the spectral lines. If we increase to 30,000, you start to be able to really define those lines. And at a spectral resolution of 100,000, which is typical of instruments like CRIROS and will be for METIS on the ELT, you'll see there's many lines in here that if we could detect them, would give us a lot of information and signal about the planet. But the key is how do we actually extract this spectrum from the observation, when really the observation will be completely dominated by the light from the host star, by at least 10,000 times brighter. And so the trick that we can use really relies on the radial velocity method, but it actually is taking the other sort of dance partner, not looking at the star, but looking at the planet itself. And so that's what you're seeing in this animation here. This is made by my first year grad student, Lennart van Slaus. And he's showing here as the planet goes around the host star, its change in radial velocity in the top plot, and in the bottom one, you can see a comparison of what the planet lines are doing. So they're Doppler shifting, red and blue shifting, whilst the lines from the host star and our own Earth's atmosphere are essentially static here, because the planet is moving on the order of kilometers per second, while our own Earth atmosphere can be effectively stationary here. And even the host star, if it's moving at centimeters per second, it's so much smaller than what the planet is doing, we can almost completely ignore it, almost. So let's actually take a look at what the spectral lines are doing over time in a more cartoon way. So just showing you again, we have our planet moving around the star. Sometimes its day side is facing towards us, sometimes its night side is facing towards us. It's moving very fast. And if we trace out what happens to its spectral lines over time, as you can see in white here, what you can actually see is that over time, you see the planet spectrum is actually tracing out its own radial velocity curve. Okay, so this is the partner radial velocity curve to what you would have measured to detect the planet with radial velocity looking at the host star. So, and what you can see here is that the telluric lines are stationary, and so what we want to do is remove everything that's not moving in wavelength in time. And then once we do that, we have just the planet spectrum. That's the hope. So what I'm going to do is I'm going to focus in on a section of this. Typically for a hot Jupiter, it would take us about one night or a half night to observe this amount of data, this window of time. And we'd get something that looks a bit like this. So I've actually flipped the axes. So now on the y-axis is time, and on the x-axis wavelength. And if there was a planet in here, if you could see it, what you would see is the lines Doppler shifting over to the blue. So they'd be going up to the top left-hand side. And the goal here now is to remove everything that's not changing in time. So removing the star, the tellurics, any continuum, and just have the planet left. And so ideally we're trying to reach the photon noise. Okay, so just the noise that's left in photon counting statistics. And the way that we do this, we start out by normalizing everything and actually removes the continuum information, which is important later. And then we apply a principal component-like analysis. This is basically just taking every column that you see here, so every pixel channel, or every wavelength channel, and it's looking for common features. And typically the first one that it finds is how the flux of the star, or the flux that you're receiving, changes with air mass. Okay, so as you go to lower and lower air masses, so you're looking more towards the horizon, it changes the flux that you're receiving. And so it tries to remove that trend scaled in some way for every column. And if we do that, we get something like this, where perhaps in the center here, we're starting to approach just the Gaussian noise left over from the photon counting statistics. But in these telluric lines, it's still really messy. And I want to show you something quickly that's important about aligning the spectra. So when I said we need stability, we want an instrument that doesn't drift in time. Now, we can't avoid drift due to the fact that the Earth is moving, and so that's going to make our stellar lines change. But if we can keep everything else very stable, that's what we want. Because if we can't do that, the effect that you would see to reach that point of the analysis, this would be if we had significant drift in our telluric lines, for example. And you can imagine if you were going column by column looking for common trends, that it would be quite difficult to find ones that fit this very well. But if I align them, you get something that looks like this. And actually that light to dark trend is actually quite easy to identify as you go across. So really aligning your spectra is quite key for this technique. But if you can do that, and you can continue to run this sort of principal component analysis, once you find an optimal number of trends to remove, hopefully you have something that looks mostly like static and the planet signal is buried in there. You can see we haven't actually hit the photon noise here, but it turns out that's actually enough. And if I was to inject a very strong planet signal in the original data, so in panel A, and do this whole process again, you would actually see the spectral lines. And so at this point, what you could do is shift these spectra into your planet rest frame, so they all align vertically, and you could sum them, and that would be your planet spectrum. However, as you can see, it's quite noisy, and I'll just show you what happens if you actually do that. So this is based on a paper from Matteo Brogi from 2012, looking at Talbot's B, which is a hot Jupiter. If the planet looks like the model spectrum, this is what we would see. But in reality, the planet spectrum looks like this. And the signal to noise here is about 1. Now, to be fair, this is a spectrum of a planet separated by only 3 milliarc seconds, which is kind of amazing that we can get that information. But if we add the noise level that we have to the model, you can see that we can reproduce this very noisy spectrum. And so it's very hard for us to distinguish the noise from the real data, although you might convince yourself that maybe you can see 1 or 2 of the CO lines that actually line up with lines in the spectrum. So what we do is some form of template matching, and in this case, cross-correlation. So we take that model spectrum and we cross-correlate it with the data, and we see where they match. And the idea here being that because that model of the different species, the different spectral lines, is so unique in the way that it's spaced and arranged, but it's very hard for noise to actually reproduce the whole model spectrum by chance. So it makes it quite a robust method to use. So that's what we do. We cross-correlate for each spectrum we had. And for Talbot's B, there were actually 3 nights of data. So every row that you see here, and by row I mean these sort of pixel rows, is a cross-correlation where the model has been run through across the data itself. And where you have a strong match, you get a slightly darker color. And hopefully you can see by this nice line that's guiding your eye that there is actually a trail here. And this is actually tracing out part of the radial velocity curve of the planet. And if we were to shift into the planet's rest frame, which we didn't know for Talbot's B because it's a non-transiting planet, but if we get it right, you can see hopefully that the line actually completely aligns. And we could actually sum that, and in a cartoon way, we would get this beautifully perfect cross-correlation function that tells us precisely where the planet is and that we've got the right velocity. In reality, we don't know that, so we actually try a whole bunch of different velocities, so orbital velocities that I've called Kp here. And we actually use those to build up each row of the next plot that you'll see, which is this one. And so each plot in there is one of those summed cross-correlation functions, each row. And hopefully you see that at about 110 kilometers per second that we get a peak in the signal. And that actually corresponds to an orbital inclination of about 45 degrees. And that just simply falls out of the binary or 2-body equations for actually getting velocities that you can actually then determine the orbital inclination despite it being a non-transiting planet. So this is the detection of CO in a non-transiting planet, and this followed the Snell and et al. 2010 detection of CO in HD 209458, which is a transiting planet. And over time, many more detections have been made. And up until the beginning of this year, I was able to, or last year, I was actually able to keep track of all of the papers on this work, but this field has really exploded. And so I've really only shown you a small selection of all of the different detections of molecules that have been made. CO was important in making the first detections. The one that came after that was actually water in H2 189733. And that showed us that we could detect more complex molecules. And then since then, there's been many, many more. So these are for detections in hot Jupiters, for transiting ones, non-transiting ones, looking both at their day side thermal emission and also at their transit. So that's the titanium oxide and the FeE2 here you can see from transiting ones. And there's a paper from Jens Hoemakers that really makes the point is that you can pick any molecule and any species in the periodic table and try to cross-correlate and see if you can find it. And that's what he did here. He tried to create a spectral atlas. And you can see the ones in green is working as a positive detection. And then in the red and the brown, it's sort of questionable or no detection. This has been really powerful. And this was looking at KELT 9b, which is one of these ultra hot Jupiters. And these are really putting all kinds of different species up in the atmosphere because they're so hot. Everything is in the gas form, so you can detect them. And you're really starting to see here the advantage of using these extreme precision radial velocity machines on even small, by comparison, telescopes. And most of the work I showed you was from cryo-res, but recently there's been more done, not in the infrared, but in the optical for transmission and emission from small telescopes like HARPS, which is one of the ones, very recent ones for WASP 121 I'm showing you here. This has actually been also shown from UVES as well, which is a slightly less stable spectrograph. It still seems to work for finding for the iron lines. So that top row is the same as what I've been showing you for the cross correlations, and the row underneath that is the cut through that shows you the actual transit depth. And actually you can see for this one, the transit depth is actually considerably deeper than what the models would suggest. In even some of the newest machines, I was very happy to see Express has managed to do this work as well, looking at Mascara 2b, again finding iron and some other species as well. So it's really exciting that all these machines can do this work. And not only can we see composition, but it also tells us about the structure of the atmosphere, especially when we're looking at dayside data. We can look for the temperature pressure profile. And I'm showing you what the temperature pressure profiles for the solar system planets look like here. You can see typically most of them are inverted. So on Earth, we know that this inversion happens because ozone absorbs UV light and that heats up a layer of our atmosphere and causes the stratosphere. And so we get this turnover here. And so the atmosphere starts to heat up again. And for example, in Jupiter, there can be some methane photochemistry, or on Titan, similar things with hazes and dust. And so in high resolution spectroscopy, it becomes very obvious when you have an inverted atmosphere in terms of temperature. So I'm showing you three temperature profiles here. The blue one is a non-inverted one, the red one is a very strongly inverted one, and the green one is sort of a little bit in between. And if we look at what the model spectra would look like in high resolution, you see we have very deep absorption lines for a non-inverted profile. But as we go towards the inverted ones, we start to see emission lines. So it really, really changes the line shape, and you can detect that with your cross-correlation. And actually this has been shown in two papers from Stefanos Nugroho in 2017 and 2018, looking at WASP 33, finding TiO and iron. And so what I want to highlight is that there's a real complementarity here between the high resolution work from the ground and slightly lower resolution spectroscopy from space. And what you're seeing here is a selection of temperature pressure profiles that all fit low resolution data, so LRS is shown there. And in that low res region, both of those profiles are not inverted. And so you might determine that the profile is non-inverted. However, as you go higher up in the atmosphere, you can see that some of them start to turn over. And if you were to look at these two red and blue lines with high resolution spectroscopy, you'd see that they're very different. And so if you could combine these two sets of information, you would be able to pin down your temperature pressure profile very strongly. And that enables you to then remove some of the degeneracy that the profile has with the composition in the atmosphere. And so that was where they were shown in Birkby and Line in 2018. And what you can see in purple there on the left-hand side is how they were able to constrain the carbon to oxygen ratio. That can tell us things about what the planet accreted from its gaseous disk. And you see it's constrained far better than either of the two data sets independently could do. And you can see the temperature pressure profile that corresponds to that. And in order to do this, they actually transferred from working with cross correlations to using a likelihood function. It actually enables us to say a bit more about the errors rather than trying to determine that from a cross correlation function. And if you're interested, the equation looks like this. This was actually modified slightly by Neil Gibson in a very recent paper. But basically, all these terms are quite simple in the end, and actually the final term is actually the cross correlation function. So it's the product of the data and the model divided by its uncertainties or variance. So it's actually fairly straightforward to calculate this. And if you do that, you can generate plots like this. So this is from Neil's paper. So in that very top left, you have one of these sort of cross-correlation matrices that we've seen before, but it's not a cross-correlation anymore. It's actually a likelihood. And then next to that, you can see the cut through at the planet detection. But then you're also able to show the distribution or the posterior distributions that come out of doing the modeling. And so here you can see how the temperature can be constrained for 3 different levels of clouds in the atmosphere. And the scaling factor alpha is really sort of an understanding of how well you know the scale height in the atmosphere, for example. So there can be quite a lot that can be extracted, even just from the high resolution spectra itself. And as I mentioned clouds, and Natasha mentioned clouds being an issue as well, in anything that we really look at for exoplanet atmospheres, at high resolution, you can actually still see the lines that stick up above the cloud deck. So what I'm showing here, even if you had a very high cloud deck, shown by this light grey line here, that everything above it would still potentially be accessible using this sort of high-res approach, which is something still to be shown in reality, but theoretically we think that this is possible. Okay, so I've shown you some of the power that it has. I want to show you a little bit of the dirty laundry before we go any further. And what really some of the issues are that can affect us. So one of the key things is that we rely on getting the model template correct in order to actually find the planet. And if the template is wrong, we're never going to find it. And I can show this by showing you what the detection of water in a hot Jupiter, if you get the lines slightly off. So this is showing you lines from a spectrum generated from the high temp database. And then these are ones coming from an old version of XML. This has actually been updated, so there's much agreement now, I think. But with the old version, you can see that some of the lines were different, and different in different ways. Some of them go to the left, some of them go to the right, some of them are different depths. So if you try to detect the atmosphere with these 2 different models, this was the one from high temp that we published in 2013. But if we use the old XML version, we find actually the signal disappears. This is just a change of a few lines. So we're really sensitive to line lists, and that can be very important, especially for some of the hottest planets. We've done a little bit of work looking at how flares can affect us. So we know Proxima Centauri, for example, can flare. It has these naked eye super flares. This is a paper from Howard et al. Showing one of those, and you can see in the time sequence that there's this, when the flare goes off, it really completely changes the spectrum. And I had a bachelor student, Lucas Stapper, look at this, and we got about 50 times more noise than in the quiescent state. So these potentially are an issue. And then something very recently that came up was looking at stellar pulsations for Delta Scuti type host stars. And so when you cross-correlate, if you're looking for something that in the planet that is also in the star, for example, iron, if your star is pulsating, it's going to cause you problems. And that's what you see on the left-hand side here. All these features in the cross-correlation plot completely obscure what would be the planet signal. And the planet signal is shown here by these different arrows as we turn over. So that's in the optical, looking at iron, but if you go to the infrared and look for CO, which is not in the host star in this case, because the host star is too hot, you can see actually that the planet signal is there. See it tracing up, but there's no contamination from the pulsations. So again, there it depends what you're looking for as to whether it causes an issue. But if we can overcome these things, we have a very bright future. So remember that I showed you for Tau Boo that the observed spectrum had a signal to noise of 1, and that was using 15 hours on the VLT with cryo-res, and that's what we're seeing in the top right here. And what we've done recently is do simulations for METIS, which will be on the ELT. And this will be the same resolution as CRIRES, obviously on a much bigger telescope. And so if we were to look at Tau Bootis B with METIS on the ELT for just 5 hours, so just taking one of these sections of cross correlations, we would get something like this. And if I just extracted the spectrum directly, no cross correlations, you would have something that look like this, where every single line here has a signals noise of 10. So actually with this, for hot Jupiters, you would actually do the equivalent of what we do now for stellar spectra to exoplanet spectra. And obviously there's much more that can be done with mini Neptunes and terrestrial planets in the same way that we've done this with giant planets so far. But for really getting that really precise work, we can do that with METIS. Okay, so I'm gonna stop here because I want to give the panel time for taking questions. But if there's time, I will talk a bit more about dynamics later. Thank you.
Okay, well, thank you very much, Jayne. It's really remarkable to see how well we can do by bringing high spectral resolution to exoplanets directly. So there are a couple of questions online. I'd like to kick it off, though, with one question that I have is, because you've lost the continuum in many cases, what can you say about absolute abundances of the various atoms and molecules?
Yeah, so I'll take you back to this paper. So this was it was a simulation, but it's for a hot Jupiter, and this was taking just CRIRES data, so you can see it in the blue. And actually you see in this case, for example, for the C to O ratio, you can actually constrain it better than the low res data, but maybe that's an unfair comparison because you're comparing CO detections to water detections, which don't have any carbon. And so there is actually, so Matteo's recent work, we're sort of approaching just with the high resolution data in terms of relative abundances the same as the transit spectroscopy from the space-based telescopes. And in absolute abundances, it helps definitely to have the continuum because that helps you set this lower temperature. So I think it's not as good, I think, for the lower resolution work, but it's pretty close. And I think there is quite a lot that we can do.
Okay, great. And let's see, online, coming back to your data analysis, Dimitri would like to know, how do you determine the optimum number of modes to subtract, and what's sort of the trade-off between subtracting the tellurics and self-subtracting the planet and so on?
Yeah.
And to what extent does resolving power come into that?
Yeah, so determining how much to remove basically is a bit of an open question. So what we're doing at the moment is we inject a planet and we run the same data analysis, and then we look at the difference between the real data and the injected planet, and we look to start to see where the analysis starts to remove planet signal, and that's kind of where we choose to stop removing the different components. Ideally, you would have a completely separate data set with no planet signal in it, and you would be able to use that as your baseline, as you would do in a transit survey where these techniques are commonly used. But for this, we sort of have to work a little bit differently. Does that cover the question?
Okay. Another question, is it possible to investigate the atmosphere of rocky planets with this technique, presumably in the future?
Yes, so that's hidden in the other slides if you want to see them later. But definitely and certainly with the ELT, so we think we'll have a good chance of doing Proxima B, which may be rocky. But we might have to slightly change how we do that, or hope that we get a transiting one. We could do this in reflected light, and that would help us look at the oxygen biosignature in the optical. So when you look at reflected light, you're actually you're not looking at a planet spectrum in your cross correlation, you're looking at the stellar spectrum because that's what gets reflected, and then it gets modulated by the planet's albedo function with wavelength. So it's a slight change on the technique. It's something that actually one of my graduate students, Eleanor Spring, is working on at the moment.